All right, so welcome back to chapter two. Here we're going to pick up on section two or part two of chapter two, where we look at the importance of water and its effect on that it has on life. And if we look at how evidence and research has suggested where life formed and began. All of that leads us to believe that life began in water and that it actually stayed in the aquatic environment and evolved there for approximately 3 billion years before it started spreading onto the land and you start getting terrestrial based organisms. And because we have this, in this deep ancestral tie to water, modern life is still heavily based on water. For example, our cells are primarily made up of 70 to 95% water, depending on the cell that you look at. The entire cytoplasm of our cell is largely made of water. The extracellular spaces around our cells are filled with a water-based fluid, um, and so our bodies are around 60% water in terms of body weight. And water is really one of the major reasons that Earth is habitable and can support life that we know of in the way that we see it today. And a lot of that, a lot of those properties, the important properties of water, really come from the polarity of the water molecule that we talked about in section one. So water having that partial polarity, those slight positive and negative charges to that water molecule that allows for that hydrogen bonding to happen. And that really is one of the driving aspects of the water properties that are allow life to exist. And so we really much so live in this watery based world, and water kind of drives everything in terms of life. And as we showed in section one, hydrogen bonding really allows for water molecules to stick together. And whenever you have water molecules sticking to one another, you have the same molecules, so like molecules sticking together, that's referred to as cohesion. So when you have the same molecules binding and sticking to one another, that's cohesion. And it's much stronger. The cohesive force is much stronger in water than what you see in a lot of other liquids because of the summation of those hydrogen bonds. And that's really important in allowing water to kind of move and transport through organisms. So, for example, trees really rely on those cohesive forces to move water from their roots to their leaves. And then also the stickiness, the cohesion of that water leads to this surface tension that is actually a measure of how difficult it is to break through the surface of the water. And again, that's because of hydrogen bonds. Those hydrogen bonds allow those water molecules to stick and hold tightly together. So it takes some force or pressure to actually break through the surface of that water. Here we have a diagram, or I'm sorry, a figure, a video that's going to show the cohesive properties of water and how it allows water molecules to move throughout vegetation.
How does water get from the roots of a tree to its leaves? The evaporation of water from leaves moves water molecules up from the roots. The evaporation exerts a pull that is relayed downward along a string of water molecules from leaf to root. Hydrogen bonds cause water molecules to stick together, a phenomenon called cohesion. As each water molecule evaporates, it pulls on the next water molecule, and it pulls on the next. This relays the pull of evaporating water molecules all the way down to the roots. The cohesion of water helps to keep gravity from pulling the water molecules back down.
And so this is a really interesting aspect because this means that the plant has to spend no energy in moving water. This is a passive process. And so the movement of water out of the leaf is driving this gradient, really, this movement of water, because that movement is pulling the water molecule out, which, like the video said, is in turn pulling the water molecules that it's connected to from the bottom to the top. And so no energy is required to move these water molecules. It's really driven by the drive of the water to move out of the leaf, which is driven by the atmospheric water content, the vapor pressure deficit, which is a really interesting aspect of the movement of water through plants. And so here we have another figure where we're looking at the cohesion of water molecules and how it moves through the xylem up to the top of the tree, again, due to the evaporation of leaves. And so we talked about cohesion as being this attraction of similar molecules, like the same molecules with one another. Adhesion is where you have molecules that are different to attach to one another. And so when you have a water molecule stick to the inside of the plant cell, that's adhesion, because the cell, plant cell, is different from the water molecules. So the molecules on the plant cell are not water molecules. So those unlike molecules that are attracted together is adhesion, whereas like molecules sticking together is cohesion. And here we have an image of surface tension that is allowing this spider, it's got a raft spider, to stay on top of the water, because the spider does not put enough force to break those hydrogen bonds between that water molecules, and it provides this what's known as surface tension that keeps that water on top of the water column. And another factor with water is, because of the hydrogen bonding, it takes a lot of heat energy, like the 2 videos ago said, to break the summation of all of those hydrogen bonds. And so even though those hydrogen bonds are constantly breaking and reforming pretty much all the time, it takes a lot of energy to break all of them at one time to allow those molecules to turn into water vapor and a gas form. And so the heat is used to break those hydrogen bonds, and so that water absorbs the heat, and it can store a large amount of heat before it warms up a few degrees. And water can then cool by releasing all that heat as well. And so it leads to a process known as evaporative cooling being able to happen. And that's basically whenever you have water come in contact with the surface of something, it can pull the heat out of the surface, and then the heat will break the hydrogen bonds of the water molecules and then evaporate into the atmosphere. And so that cools that object down while transferring that heat out of the object. And then when you have water molecules to get cold enough, they will actually form ice, as we all know. So basically what happens is, in liquid water, your water molecules are moving all around, kind of doing like this and reforming hydrogen bonds and breaking hydrogen bonds. And they're really densely packed together, and that's what leads to that liquid state at room temperature. However, whenever water cools enough, it freezes, and you basically have the water molecules stay at even distances from one another, and those hydrogen bonds become stable. And because they're not as dense as the water molecule, ice floats on top of water. So you can see in this image how the liquid water molecules are really densely packed together, whereas in the frozen ones, where those stable hydrogen bonds are, they're more evenly spaced, leading to less dense type of mass. And so that again is why ice floats on water, and this is really important, okay? Because if ice did not float on water, then ice could form throughout the entire water column. And you wouldn't end up with this situation where ice floating on top of water basically serves as a blanket, like we say here, allowing life to persist under those frozen environments. So if it didn't float, then the ponds and oceans would freeze solid and the life that existed underneath the ice would die. It wouldn't be able to live unless they evolved a certain mechanism to allow them to go dormant until the water thaws out, which would be pretty amazing. There is some organisms that can do that, but again, we wouldn't see as much diverse life in, maybe we would, in these environments. They would really have to be specialized. Water also is what we call the solvent of life. Basically, water can dissolve a lot of different atoms and molecules and transport those around the body, around through different organisms. For example, you have a solution, which is a liquid that is made up of a solvent and a solute. So a solvent is what dissolves the solute. So if it's water that is dissolving a solute, then it's known as an aqueous solution. So for example, salt dissolving in water or sugar dissolving in water, that would be this aqueous-based solution. And the way that water dissolves these solutes is those partial polarity in the water molecules interacts with the molecules that it's dissolving. So for example, salt we know is sodium chloride, which are two ions bound together in a chemical bond. These water molecules also have a partial charge, and so the negative charge in the oxygen can interact with the positive sodium ions and kind of pluck them from the crystal, and the positive charged hydrogen portion of the water molecule can interact with the chlorine ions and pull them out of the crystal, dissolving that salt crystal away as the water pulls all of those atoms out of that salt crystal. And so that's how it pretty much dissolves a substance or a solute. Water is also important because it can be acidic or basic, or it could have what we call a neutral pH. And that is based off of how many hydrogen ions are in that water solution. If there are a lot of hydrogen ions, then it's known as an acidic solution. If it has more OH hydrogen molecules, low hydrogen ions, then it's a basic solution. And if you have a compound that releases hydrogen ions into solution when it dissolves, then that's known as an acid. If it takes up hydrogen ions and removes them from solution, then it's known as a base. So acids make a solution more acidic because they release more hydrogen ions into solution, resulting in a higher hydrogen concentration. And the way we describe this acidity of a solution is through the use of a pH scale. So we can say this solution has a pH of 2, then it would be really acidic. Has a pH of 14, then it's really basic. If it has a pH of 7, then it would be a neutral pH. The hydrogen ions would equal the OH ions. And organisms will have buffers, and specifically in humans, we have carbonic acid and bicarbonate, which are buffers to take up and release hydrogen ions to regulate the amount of hydrogen ions that exist in solution. So here we have an example of a pH scale where 7 is neutral. So again, hydrogen ions equal the concentration of hydroxide ions. And then as you go down in pH, you get more acidic, you get more hydrogen ions in concentration compared to your hydroxide. And then as you go basic up in pH, your hydrogen concentration goes down and your OH concentration goes up. So some examples of acidic components or solutions are things like battery acid, lemon juice, your stomach acid. Coffee is somewhat acidic. Urine is somewhat acidic. Basic solutions are things like seawater, ammonia, bleach, oven cleaner, etc. And then your blood and pure water are around neutral, so around the 7 range. Pure water should be neutral. Your human blood should be close to neutral in the 7 pH range. One thing that's important to know with this pH scale is that this is a log scale. So that means, so we'll say it's a log scale. So that means that every change in 1 unit of a pH scale is a 10 times change in the hydrogen concentration. So for example, if you change from 8 to 7 on the pH scale, the hydrogen concentration has changed 10 times. You've changed 1 unit on the pH scale, which is a 10 times change. If we go from 8 to 6, we've changed 2 units. So that's 10 times 10, right? So it's now in a product. So this means that it's a 100-fold change. When you go from 8 to 6, you have a change in the hydrogen concentration of 100 times. If you go from 8 to 5, we've changed 3 units, so that's 10 times 10 times 10. So that's 10 times 10 is 100, 100 times 10 is 1,000. So that's 1,000 increase in the amount of hydrogen ions. And I said increase because we're going down in pH, and as you go down in pH, your hydrogen ion concentration increases. If we were going from 8 to 11, which is 1, 2, 3, you would have 1,000 change, but you would have a 1,000 times decrease in the hydrogen ions because you're becoming basic, okay? So for example, a question on your exam or quiz related to this could be, you have a solution. It started out at a pH of 14, and your final pH of this solution after 2 hours is a pH of 12. What is the overall change of the hydrogen concentration? So basically with this question, you're going from 14 to 12. So that's 2 unit change. So that's 10 times 10. So that's 100 times change. So we know it's 100 times. Now we have to determine whether or not it increased or decreased in hydrogen ions. We're going down on the pH. So that means it's an increase in hydrogen ions. So we have a 100 times increase in hydrogen ions when we go from a pH of 14 to 12. Okay, so you want to make sure you can answer your questions in that way. Here we have another figure of this, which is the neutral solution. So those are equal. Basic, you have more OH than hydrogens. Acidic, more hydrogens than OH. Here we're showing an example of acidification happening. So for example, carbon dioxide can go into the oceans. They can interact with the water. So CO2 and water, these two reactants will make the product carbonic acid. And this carbonic acid can break down and shed off a hydrogen ion. And when it does that, the water will become more acidic, and that increase in acidity is really bad for the corals that we see here, because the zooplankton, the algae that live inside the corals that give the corals their food, can't survive in that pH. And so the algae will leave out of the corals. Corals no longer have food, and so the corals will die, and that's what coral bleaching comes from. So the increase in CO2 dissolves in the water, causes that acidity in the oceans to increase, therefore leading to coral bleaching events. And so here's another question that you can look at. So compared with a solution of pH of 8, the same volume has a pH of 5. This has blank times more hydrogen ions. The second solution is considered a blank. So just pause this, take a minute to answer this question. All right, so what you should have gotten is a pH from 8 to 5 has 1,000 times more hydrogen ions. You have 10 times 10 times 10 because you move 3 units. And then the solution, because we are lower in the pH scale, is acidic. So it would be 1,000 times and acidic. Okay, or it would be considered an acid. Sorry for the bad handwriting. Okay, and so that's it for section 2, and this is the last video for your chapter 2 module. So you'll just want to make sure you complete your lab exercise for the week, and you complete your lab quiz for the week as well. So your lab exercise is found on Top Hat. Your lab quiz will be found on Canvas, and then you want to finish your self-check for the module, and you will be good to go for the chapter 2 material. So we will pick up in the next module looking at chapter 3, and we will see you all there.